Using Gauss Jordan elimination method to solve a system of equations. Begin with the algebraic format of the system. The objective of Gauss Jordan is to transform the matrix on the left to be an identity matrix, and the augmented right hand side will be the solutions to your x, y, and z. Okay, so let's begin. Start with column 1 and check whether the elements are already according to the identity matrix. So 1 is completed, it's already in position. We want to make 2 and negative 2 into zeros. So what number will make 2 a 0? 2 will have to be added with negative 2 equals to 0, and we can use the diagonal 1 just now as the vehicle where we can write on it to make it, to add it to 2 in order to get 0. So I'm going to use row 1, multiply it with negative 2, and then come and add to row 2. Same process. What does it take to make negative 2 0? Will be to use 2, which is multiplied on another number and added to negative 2, which is now in row 3, and you can get 0. So the contra number will be 2R1 as the neutral vehicle plus row 3. The result of this will be row 1, we just copy as it is, no operations there, but row 2 will be negative 2 times row 1, negative 2 times 1 is negative 2 plus 2 is 0. Negative 2. Okay, so we've accomplished what we wanted to do, which is to get 0 for that column and that position. Now we will have to use the same operation for the rest of the row. Okay, for the rest of the row. So we repeat the same operation, which is negative 2 R1 means negative 2 times negative 1 is 2. 2 plus 3 will be 2 plus 1 will become 3. That's the second element in the row. The third element in the row, same process, negative 2 of R1, which is 3, so you get negative 6. Negative 6 plus 2 will become negative 4. The last element here, negative 2 times 2 plus 2 is negative 4 plus 2 will be negative 2. And in the next row, we do the same process, 2 times R1, which is here. So 2 times R1 and then plus R3. So that's 0. We do the same, 2 times R1 and then plus 3, row 3. We get negative 3, 2 times R1 plus R3. We will get 7, 2 plus R1, 2 times R1 plus R3. It's another 7. So column 1 is clean. Now we move on to column 2. And again, we always start with the diagonal element, which is 3. What would it take to make 3 1? Will be to multiply it with 1 over 3. So this is what we're going to do to row 2. No change in row 1 and no change in row 3. But row 2, remember all the other members of the row or elements in the row will go through the same operation as the targeted number. Okay, although we target just for this number, but the rest of the row will go through the same operations. Now, the 0 elements in the column can be simultaneously eliminated, just like what we did in the first step. We do the two zeros here in one shot, right? So same thing, you can do the 2 zeros here in one shot. Find what will be the counter number. So in this case, it would be 1. So you use the diagonal number and bring it to row 1, which is the target row. Same thing with this row, negative 3. The counter number is, or the opposite number will be 3. Use the diagonal element in row 2, bring it to row 3. So what you're trying to do again is here is 3 times 1 plus negative 3. If you're not sure, right? Okay, so let's start. Row 2 is the same. Row 3, do the same process as we have decided, because we want this to be sorry, let's go back one step. Okay, so 4 over 3, this is row 2, 4 over 3 plus 3 is 5 over 3. So you need to do side calculations here. Negative 4 over 3 times 1 plus 3. So 3 will be 9 over 3, and that gives you the 5 over 3. So a simple calculation on the side will give you the number. You do the same thing, you should get 4 over 3 here. For 3, piggy right on row 2. So 3 times negative 4 over 3, and then bring to 7. Same thing with this. 3 times 2 over 3, negative, you get negative 2, bring to 7, get 5. Okay, take your time, but make sure you do the side calculations accurately as well. So we've accomplished column 1, column 2. Now we move on to target column 3, and we start with the diagonal element here, which is 3. Again, multiply with 1 over 3, and we should get matrix Okay, now we are ready to divide, get 1. And then, since we're doing the same operation for all elements in the same row, so that's your number. The next target will be the 2 0 elements in column 3. So the number that you need to counter negative 4 over 3 will be positive 4 over 3 using row 3, and you add to the row 2. For first row, the countering number will be negative 5 over 3 of row 3 as the vehicle which you brought to row 1. So now the results will be 1, 0, and because you designed the operation to suit what you need for this element, then it should be 0. Now for the last element, the side work will be what happens to when you have negative 5 over 3 times row 3, which is also 5 over 3, and then add to row 1, which is 4 over 3. So that makes it 9, negative 25 plus, make it into a 9 denominator as well, and you would have 12. So negative 13 over 9. So that will be the answer. Same thing with row 2. You already have 0, have 1, that will not change actually. And this is also designed to be 0. So you need to worry about 4 over 3, multiply with row 3, but added to row 2. So that is a 9 again, 20 plus, so you make it another 9 and you have negative 6. So that is a 14 over 9. The last row does not require any additional change. So you have, this is your final set where x equals to 13 over 9, y equals to 14 over 9, and is that we are taken from here, no other variables in the middle, so 9. finished. If you have mastered Gauss Jordan, you can solve a system of any form, and you can easily pick up the answers from the final Gauss Jordan matrix that you got. For instance, here, if the final step is, or the final matrix is as such, you end up with a 0, 2, and negative 1. So you couldn't finish it. You couldn't cleanly clear column 3. You can stop there and start interpreting your answers. So you have here x, no y, but 1 negative z. The second row gives you y plus 2z equals to 4. And the third row, which is supposed to specify z, does not say anything about z. So you can say that z is all real numbers. You can even simplify it to x equals to, from here, 1 plus z, y equals to 4 minus 2z, and z itself is all real numbers. Another possible case that you have and again you can say that x equals to 1 plus z, which is the same as above, y equals to 4 minus 2z, but here you meet with the dead end because 1 can never be equals to 0. I'm sorry. Okay, z is not specified, but 0 y, 0x, 0y, 0z could not be equals to 0. Equals to 1. So in this system there is no solution to the system, right? This one you can have multiple, or in fact infinite number of solutions. Next, we are going to look at matrix Gauss Jordan. The concept of inverse. Now, why do we need inverse? Because in matrix world, you cannot divide A. You cannot divide AB this way. What you need to do is find the inverse of B and multiply it with A. So this is the matrix rule, or the matrix notation. if your matrix is 2 by 2, then there is a simple way the inverse of the matrix would follow this structure. D will come up, A switch places, and on this diagonal it will be negative. Example, six minus 30, A D minus B times C, and the matrix itself will take that switch. So 2 and 3 switch 5 negative 6 negative, and it will be negative 24 2 negative 5 negative 6 and 3. So your matrix inverse is negative 2 over 24 negative 5 over negative 24 negative 6 negative 24 3 over negative 24, which you can simplify further. Okay, a 3 by 3 matrix requires a Gauss Jordan in which you can put up a matrix on the left, let's call this the A matrix, and set up an identity matrix on the right of the augment, call this the I matrix. Then you can do the row operations necessary, column by column, 1 0 0 1 0 0 1 0 1 0 0 1 0 0 1 0 0. Yeah, for example, you can choose whatever necessary operations needed here, and so on and so on and so on. The idea is to use Gauss Jordan to obtain the solution matrix whereby the identity is on the left and the inverse will be on the right through your Gauss Jordan. That's all for this time.